Okay, so we have seen in the last lecture how to construct the universal covering for a given topological space, and now we go back to looking at coverings of Riemann surfaces. So see, so far whatever I have discussed about the coverings of a space, they were all in the topological category. Okay, so the maps involved were just continuous, and therefore, and also the isomorphisms that were involved were all homeomorphisms. They are isomorphisms in the topological category. I just want to say that all these things will now go on into the domain of the holomorphic category. Okay, so what I am going to do basically in this lecture is try to explain the holomorphic theory of coverings. Okay, the theory of holomorphic coverings, right. So what I do is start with a covering, x tilde to x. Okay, so this is a of course when I say covering I mean topological covering. Okay, topological covering. Right. Now I am going to look at the situation when this the base of the cover, okay, has the structure of a Riemann surface. Okay, so suppose x has a Riemann surface structure which let me call it as x sub whole. Okay, so x is the topological space, but x sub whole is this topological space endowed with the Riemann surface structure, which means you know what it means. It means every point of x is given a coordinate chart. Okay, it is given a chart that is a neighbourhood which is homeomorphic to an open subset of the complex plane. Okay, and all these charts, any two such charts that intersect are compatible, namely the transition functions are holomorphic, and of course when I take the Riemann surface corresponding to this, I mean I include all possible compatible charts, so I take the maximal atlas. Okay, so that is what I denote by x sub whole. Alright, now what I am going to explain is that this x tilde naturally gets again a holomorphic structure, okay, and makes this into a Riemann surface, and this map becomes holomorphic. Okay, all this happens very naturally just because P is a local homeomorphism. Okay, so so now what I am going to do is I am going to try to give charts on x tilde. So we make x tilde into a Riemann surface x sub whole, x tilde sub whole as follows. So what I am going to do is, so again let me draw a diagram. So you see I have x tilde here, and I have x, this is P, and here is my x, and well I take a point of x tilde, small x tilde. Okay, then you know pretty well that if I take the image of this point below and suppose I call it as x, so P of x tilde small x tilde is small x, then you know that because this is a covering, okay, in fact I do not even need its covering, but anyway it is a covering, I can find a neighbourhood, an admissible neighbourhood for x. So if I call that admissible neighbourhood as U, okay, then its inverse image, the inverse image of this admissible neighbourhood under P will give you several copies of this neighbourhood above, and exactly one of them will contain x. Okay, so what I will get is I will get a U tilde which is one of these copies. Okay, so for this I need not even have taken a admissible neighbourhood below. In fact, even if I knew that this is not a covering, but if I knew only that it is a local homeomorphism, I can always take an open set above which is going to be mapped homeomorphically onto its image below, which is an open set by this map P. Okay, so I am saying that I can do this even if P is a local homeomorphism. Okay, so in any case we can choose an open neighbourhood, open set u tilde containing x such that P restricted to u tilde from u tilde to P of u tilde, which is u, is a homeomorphism. Okay, I can do this. I can do this even if P was just a local homeomorphism at the point x tilde. Okay, and now you see the space below x has a Riemann surface structure. Okay, so let me write this as x sub whole. Okay, let me write this as x sub whole just to tell you that there is a Riemann surface structure below. So that means at every point there is a chart, there is a coordinate chart. So what happens is that I can find, so there is an open neighbourhood of this point, let me call that as V. Okay, I have an open neighbourhood of this point and I have a chart, namely a function from this into a phi which goes into phi of V, which is an open subset of the complex plane, and phi is a homeomorphism. Okay, so this is just the chart at the point x, because the space below has a Riemann surface structure. There is a chart given at each point. I am taking a chart v comma phi, okay, which contains the point x. All right, so take a chart v comma phi such that small x belongs to V, where small x is the image of x tilde. Okay, now you see, if I look at this intersection, this intersection, okay, so let me shade it. This point is x. Okay, this shaded region is V intersect u. Okay, if I take this V intersect u and if I take its inverse image under P restricted to u tilde, what I am going to get is I am going to get again here, I am going to get a shaded region here. Okay, and of course my point x tilde will be here. Okay, and from u tilde to u it's a local homeomorphism, P restricted u tilde. So restricted to this shaded portion will also be a homeomorphism. All right, and if you combine that with this phi, I will get a chart in this neighbourhood for the space above at the point x tilde. Okay, so then, so you know how do I write that set theoretically? I just take first of all the intersection of V and U, which is the shaded portion here, V intersection U. Then what I do is I take its inverse image under P restricted to u tilde. Mind you, I can write inverse because P restricted to u tilde is a homeomorphism, so I can write the inverse. Okay, so that gives me this shaded region. Okay, that is an open set containing x small x tilde. Okay, and I have to and the map I take is P followed by phi. Okay, so P followed by phi. This of course P followed by, when I say P followed by phi, that restricted to this shaded region of course. Okay, then this becomes a chart at x tilde because it is this is a homeomorphism followed by another homeomorphism. Okay, so it's a homeomorphism into an open subset of the complex plane, so it's a chart. Okay, so basically what I'm doing is I'm I am pulling back charts from below, I am just pulling back charts from below, alright. Okay, so then this is a chart for at x tilde. Okay, now it's kind of pretty clear that all charts of this type they are going to be compatible. Okay, and the reason is that the if you write it out, the transition functions are going to be actually the transition functions for the charts below. Okay, so and once we know that, then you know that x tilde has a Riemann surface structure. Okay, which is what I am going to call as x tilde subhole. Okay, so let me write this down. So well, two such charts. So instead of doing that, let me if we had chosen another chart p prime comma phi prime at x, okay, instead of v comma phi, suppose I chose another chart, okay, then the transition function for the pair this chart, namely so this chart, so p restricted to u tilde, well, inverse v intersection u comma phi circle p, and a similar thing that you will get with by pulling back the chart v prime comma phi prime comma p is, what is the transition function? The transition function is just this followed by that inverse, okay, or that followed by this inverse. Okay, so if you give me a pair of charts, there are two transition functions. Okay, they are going to be both homeomorphisms, and the condition for compatibility is that these should be actually holomorphic. That is your condition. Okay, when do we say two charts are compatible? Okay, we say two charts are compatible whenever they intersect. Okay, that intersecting open set is mapped by both of these chart maps to different domains onto the complex plane, and then the map from this to one of these domains into the other, okay, which is given by taking inverse of the map corresponding to one chart followed by the map corresponding to the other chart. You want that not only, that will of course be a homeomorphism, you want that to be holomorphic. That is a condition for compatibility of charts. Okay, so what will happen is, in this case the transition function will be phi circle p, well, the inverse of one followed by the other, or of course or its inverse, okay, depending on which order you take it in, alright. But what is this? This is just, if you write it down, it's phi circle p inverse circle phi prime inverse, so you will simply get phi circle phi prime inverse. Okay, but what is this? This is a transition function for these two charts, the pair v comma phi and v prime comma phi, and that is holomorphic because they are compatible, because they define a Riemann surface structure below. Therefore you see the way that you have given the charts, automatically they will be compatible, okay, and you will get a holomorphic structure, Riemann surface structure on x tilde. Okay, why it will still be a surface is because you see it's a local homeomorphism. Okay, so dimension is not going to change. Okay, locally they are isomorphic, so this, if this is a surface, that's also going to be a surface. Alright, so which is holomorphic since it is the transition function for the pair of charts, the pair v comma phi and v prime comma phi prime, which are compatible. okay. So the moral of the story is that all the charts that we are going to get, they are going to give you they are all going to be compatible, and therefore x tilde will get a Riemann surface structure which I will call as x tilde sub hole, okay. Thus x tilde gets a Riemann surface structure which I will call as x tilde sub hole, okay, alright. Now so you see what has happened is that the Riemann surface structure below has been transported to a Riemann surface structure above, and that has been done by this map because it is a local homeomorphism. I do not think I am even using that it is a covering, alright. The only thing I need is that it is a local homeomorphism, alright. Now once you do this, you see the beautiful thing that happens is once you do this, so you can think of P as a local homeomorphism. It's a map from x tilde hole to x hole, and then the beautiful thing is that P becomes holomorphic, okay. But you see, if it's holomorphic and locally homeomorphic, that means it's holomorphic and locally injective and open, okay. In fact it's holomorphic and locally injective, okay. But you know, injective holomorphic map is open, an injective holomorphic map is open, and it is biholomorphic. So what will happen is that P will not only become holomorphic, it will become locally biholomorphic. So the local homeomorphic, P being a local homeomorphism, that property will immediately give you that P is a local biholomorphism, okay. And therefore what happens is that if you give me an admissible neighbourhood below, okay, then of course you take the inverse image of this admissible neighbourhood, it's going to break down into neighbourhoods above, okay, open sets above, such that P restricted to that is not only going to be a local, it's not only going to be a homeomorphism, it will actually be a holomorphic isomorphism, it will be a biholomorphic map, okay. So what will happen is that this whole covering will become completely a covering in the holomorphic sense, okay. So just because the fellow here, the base space here is a Riemann surface, okay. So that is what I want to stress upon. So with this Riemann surface structure, P from x tilde hole to x hole becomes holomorphic, okay. Why does it become holomorphic, okay? How do you check that? You see, normally, you know, if you give me let me use y1 and y2, suppose they are Riemann surfaces, okay, and F is a map from y1 to y2, when do you say that F is holomorphic, okay? The method is that what you do is that you check F is holomorphic at each point. So first of all F has to be continuous, okay. So y1 comma y2 Riemann surfaces, F continuous map, F is holomorphic if it is holomorphic on a cover of y1, okay, to check to check properties like continuity, differentiability, etc. Nice properties, it's enough to check them on a cover, okay, if you want to check them on the whole space, alright. So if I want to check a map is holomorphic, I can check it, check that it is holomorphic with respect to an open covering. And what covering do I take? I take the covering of charts, okay. I take a chart here, I take a chart there, okay, and I check. And how do I check? Well, you can even check it point wise, okay. So if y1 is a point of y1, and if it goes to a point y2 which is f of y1, okay, for example, to check f is holomorphic at y1, what do you do? Well, you do the following thing, you take a charge centered at y2, okay. Let uh, let us say V2 comma phi2 be a chart centered at a chart, let me say, when I say centered I mean containing a chart at y2 for the Riemann surface below, alright, and consider a chart V1 comma phi1 with you know f of V1 going into V2, okay. So I can do this, you see V2 is an open set which contains y2. By continuity I must be able to find an open set V1 of y1 which goes into y2, that is just because of continuity, okay. And then I can it can be it will have there will be a chart, if you maybe I may have to shrink y1 if necessary so that I get a chart, okay. So once you fix this, how do you check that the map F is holomorphic? So what you do is you do the following thing. So you have y1 here which is sitting inside V1 which is an open sub of y1, and f is going to go from y1 to y2, it is going to take V1 to V2, okay. This is also open and this contains y2, okay. Now you see from V1 there is the chart phi1, okay. So what is going to happen is from V1 to so you have phi1 which is a homeomorphism onto phi1 of V1 which is an open subset of the complex plane, okay. And well from V2 to phi2 of V2 you have this phi2 which is a homeomorphism onto phi2 of V2 which is an open subset of the complex plane, okay. And now what you do is you go like this, namely you apply phi1 inverse, okay, then apply f and then apply phi2, okay. This will give me a function from an open subset of the complex plane to another open subset of the complex plane, and all I have to do is I will have to check that this function is holomorphic. If I want to check f restricted to V1 is holomorphic, I have to check that this function is holomorphic, that is the definition, okay. And if I want to check f is holomorphic at y1, I will have to check that this function is holomorphic at the point that y1 goes to here, okay. So let me write that f is holomorphic if and only if phi2 circle f circle phi1 inverse is holomorphic, okay. This is the definition of a map being holomorphic, okay. You check the holomorphicity in terms of local coordinates, local charts, alright. Now play this game with this situation and you will see it is very trivial, okay. Let us play this game with that. So what is happening is you see I have this shaded neighborhood, so let me redraw that diagram there. So you see I have this shaded neighborhood above, okay, and this shaded neighborhood is just so let me so this shaded neighborhood is I guess u tilde p restricted to u tilde inverse of v intersection u, okay, and then there is this map p from that into the space below, into the open set below, and this open set below is just v intersection u, alright. And from here I have the phi which is the chart below, v comma phi is the chart below, alright, and it is going to take v intersection u to phi of v intersection u, which is of course an open subset of the complex plane, okay, and this is a homeomorphism, okay. And on the other hand, what is the chart here? The chart here is nothing but, I mean the chart here is actually this followed by this, okay. So the chart is here is just if you look at this definition, it's phi followed by p, okay. So the chart above is p followed by phi, okay. And what is its image? Its image is the same thing. You apply p first to this shaded piece, it will go to this shaded piece, and then apply phi, you will get this. So what I will get here is again phi of v intersection u, okay. And if I write out this map as I have written it out here, you know, this map will just be the identity map, okay. This map will just be the identity map, because it will be if you go by this definition, this map is going to be what is this map? This is going to be phi circle p inverse followed by p and then followed by phi by this definition, okay. And what is this? This is exactly identity, so this is just identity map, okay. And the identity map is of course holomorphic, okay. So trivially the projection, the map P becomes holomorphic, okay. So it's just I mean without no extra effort, it just comes just like that, okay. So the moral of the story is therefore P is a holomorphic map, okay. So it's very clear. So identity map on any open subset of C being holomorphic, P restricted to this set, let me call this as or let me write it in words, P from the shaded region is holomorphic, okay, alright. So but I can cover the space above by such shaded regions, so P will be holomorphic everywhere, okay. To check something is holomorphic, I have to check only on a cover, okay. So P restricted to the shaded region is holomorphic, and that will imply that P is holomorphic. In fact what it will tell you is its P is locally holomorphic, okay. If a global map is locally holomorphic, then it is holomorphic, okay, because that is I mean that is one of the good properties of I mean in fact that is how good properties will behave, okay. To check something is continuous, you check it's locally continuous, okay. To check that a map is continuous, you check it's locally continuous, okay. And the same thing holds for something being holomorphic, okay. Holomorphicity is a good property, you can check it on an open cover, right. So okay, so now so what is the upshot? The upshot of this is that now since an injective holomorphic map is a biholomorphic map, what this will tell you is that this is actually locally biholomorphic, okay, and therefore this is actually a covering in the holomorphic sense, okay, right, which means you take any admissible neighborhood below, the inverse image will break down into a disjoint union of open sets, not only restricted to which P is a homeomorphism, it will actually be a holomorphic isomorphism, namely it will become restricted to each of these pieces above, P will actually be a biholomorphic map. So it is completely in the holomorphic category. So you get a holomorphic covering, right, this becomes a holomorphic covering, okay. So let me write that down, thus P from x whole sub tilde to x sub whole is holomorphic, and P being locally injective, okay, because it's local homeomorphism, P is locally injective, we get it is also locally biholomorphic, which means locally a holomorphic isomorphism, okay. P was in the topological case, P was only locally a topological isomorphism, namely a homeomorphism. Now everything has transferred to the holomorphic category. So what has happened is that P is locally even a holomorphic isomorphism, which is what we call as a biholomorphic map, okay. So it's also locally biholomorphic. Thus P from x whole tilde to x whole becomes a holomorphic covering, okay. Now what I want to say next is that I want to say that the okay, so I want to say the following thing. I want to say that, you see, I want to say that any other Riemann surface structure on x tilde that makes P into a holomorphic map has to be none other than this one. So what I am saying is that you cannot get another holomorphic structure on x tilde that converts it into a Riemann surface in another way which is not the same as this. So there is this rigidity, I mean the under this if you want P to be holomorphic, okay, then there is only one Riemann surface structure on the covering, okay, it is unique, okay, that is what I am going to prove, right. So so claim if x whole, let me put prime, is another Riemann surface structure on x tilde sub x tilde such that P from that structure x tilde sub whole prime to x whole is also holomorphic, then I am right, I'll put then they are then x tilde whole prime has to be equal to x whole prime tilde, okay. In other words, there is only one Riemann surface structure on x tilde which makes P holomorphic. There is only one, there is a unique Riemann surface structure on x tilde that makes P holomorphic, okay. In other words, there is a unique one and only one Riemann surface structure on x tilde that makes P holomorphic, okay. So this is the uniqueness of the Riemann surface structure that you get above. So you see, when you take a covering, topological covering, if the base space has a Riemann surface structure, that dictates the Riemann surface structure on the cover, okay. So that is the that is what happens, okay. So how does one see this? So one sees this as follows. So to see this, I just again let me write down a simple exercise. Yeah, so I will make an observation. Let Y be a Riemann surface. Let Y be a Riemann surface. Okay, let Y be a Riemann surface. So that means Y is given with a maximal atlas, okay, of consisting of all possible compatible charts, collection of compatible charts, okay. A chart u comma phi where U in Y is an open set is in the Riemann surface structure that is belongs to the maximal atlas that contains all possible mutually compatible charts. Okay. So, I have a Riemann surface and I have a chart. The question is, when is this chart in that Riemann surface? In that Riemann surface means in the maximal atlas defined by the Riemann surface, and I am saying the condition is just phi has to be holomorphic. Okay. Then so I have not completed my statement. A chart U comma phi where U in Y is open is in the Riemann surface structure if and only if phi from U to phi of U, which is an open subset of C, this is a homeomorphism, okay, is holomorphic. So this is my remark. So please try to understand what I am saying. I am saying Y is a Riemann surface, alright. U is an open subset of the Riemann surface and phi is just a homeomorphism of U into an open subset of the complex plane. Okay. When will this also be compatible with every chart that defines the Riemann surface structure on Y? That is the question. I am saying that will happen if and only if this phi itself is holomorphic. Okay. So if you remember, I told you that one way is I told you why one way is very easy. Okay. So what is the proof for this? The proof for this is if U comma phi is in the maximal atlas for Y, then clearly phi is holomorphic. Okay, because if you remember, I told you long back in one of the earlier lectures that you see, how do we define a Riemann surface? We first define a Riemann surface by giving a cover by charts, and the charts are only homeomorphisms of open subsets of the surface into the complex plane. The only condition you put is that the transition functions are going to be holomorphic. Okay, but then I told you once you have defined the Riemann surface structure, then the coordinate map given by each chart, that itself becomes holomorphic. Okay, so if U comma phi is in a chart, is in this maximal atlas, then clearly phi is going to be holomorphic. I will have to prove the other way around. Okay, so I hope you have already done this exercise. All right. Conversely, suppose phi is holomorphic. Okay, conversely suppose phi is holomorphic. I will have to only check that U comma phi is compatible with every other chart that intersects it. Okay, so we only have to check that U comma phi is compatible with every other chart, every chart U prime comma phi prime in the atlas, in the maximal atlas for Y. Okay. In fact, you need not check with a maximal atlas, you can check with an atlas which consists of a covering. Okay. So why is that so? You can easily check it. So let me write that down. So you have the situation. The situation is like this: you are on y, okay, and there is this u, and there is a phi which is a homeomorphism into phi of u, which is open, which is an open subset of the complex plane, okay, and there is you are given another u prime which is also an open subset, and a map phi prime which is homeomorphism onto phi prime of u prime, which is again an open subset of the complex plane, okay. And how do I what is the compatibility of u comma phi with u prime comma phi prime? I will have to take this intersection, okay, and I will have to write out the transition function and say that that is holomorphic. That is my condition. So what is the transition function? So the transition function is going to be like this. So this is going to go to phi of u intersection u prime, and here it is going to go to phi prime of u intersection u prime, okay, and my transition function is going to go like this. What is the transition function? It is just apply phi inverse and then apply phi prime. This is my transition function. And when are these two charts compatible? When this is holomorphic, when this is holomorphic. So that is what I have to check. I have to check this is holomorphic. But what is given to me? What is given to me is that phi is holomorphic, okay. So phi is holomorphic, therefore phi inverse is also holomorphic, okay. Phi is holomorphic and phi is injective, so it is biholomorphic. So the inverse is also holomorphic. So this is holomorphic, and phi prime is holomorphic because u prime comma phi prime is already in the atlas. Anything in the, you take any chart in the atlas, the coordinate map for that chart is holomorphic. So phi prime is also holomorphic, therefore this composition is holomorphic. So I have checked the compatibility, alright. So phi holomorphic implies phi inverse holomorphic, u prime comma phi prime in the atlas for y implies phi prime is holomorphic. So phi prime circle phi inverse is holomorphic, okay. So this completes the proof of this claim, alright. So let me again sum up this observation to check that a chart belongs to a Riemann surface structure. All you have to check is that the coordinate map of the chart is holomorphic, nothing else, okay. Now keep that in mind, and I will tell you why there is only one Riemann surface structure on x tilde that makes P holomorphic. So let me run this. I hope I won't need it again, but okay. So now let's apply this observation to this map. So what is given is yeah. So you see, coming back to our situation, so I have x tilde whole to x whole. This is P. This is already holomorphic, all right. And what is given is that there is a x whole prime. This is another Riemann surface structure on x tilde, and then this is also holomorphic, okay. Now what I am going to do is I am just going to take the identity map, okay. Take the identity map, this diagram commutes, okay, because this is just identity followed by P is just P said theoretically, okay. Just take the identity map of x tilde. The identity map on x tilde is of course it's of course a homeomorphism, no doubt about that, okay. The point I want to make is that this identity map on x tilde is locally biholomorphic, that is because you see this is locally biholomorphic and this is also locally biholomorphic. So you know I can go from a neighbourhood here to an isomorphic holomorphically isomorphic neighbourhood here, and then I can go to go back to the same neighbourhood under this map. Okay, so what this will tell you, P both these P's being locally biholomorphic, okay, will tell you that the identity map on X tilde is locally biholomorphic. Okay, that means identity map itself is holomorphic. Okay, I told you if a map is locally holomorphic then it is holomorphic. Okay, so P being locally biholomorphic implies that the identity map on X tilde is biholomorphic. Okay, so is biholomorphic and in fact it gives you a holomorphic isomorphism from this to that. Okay, that is gives a holomorphic isomorphism from X tilde whole to X tilde whole prime. Alright, now this should tell you that these two are the same. If you have any doubt, you just have to apply this. So what I will do is let me take any chart there and tell you it is already here. Okay, see if let me say W tilde comma phi tilde is a chart in the atlas for this guy X tilde whole prime, then you see then phi tilde from considered as a map from W tilde considered as an open subset of X tilde whole, okay, to phi tilde of W tilde is also holomorphic. Okay, why? Because you see what is happening is you have X tilde whole and I have my W tilde, okay, then I have this identity map on X tilde which is holomorphic, and that will carry W tilde back to itself as an open subset of X tilde whole prime. Okay, and of course since phi tilde is a coordinate map for a chart which is in X tilde whole prime, this map, this is phi tilde into phi tilde of W tilde, this is holomorphic. Okay, this map is holomorphic. That is because phi tilde W tilde comma phi tilde is a chart for X tilde whole prime. Okay, so this map is holomorphic. This map is just the identity map, and we have checked that is already holomorphic. Okay, and so therefore the composition, okay, the composition is just phi tilde considered as a map from W tilde as an open subset of X tilde whole. Okay, that is also holomorphic, and therefore by this observation you get that this chart is also in X tilde whole. Okay, so you see so this implies that W tilde comma phi tilde is in the atlas for X tilde sub whole. Okay, so the moral of the story is that these two are actually equal. Okay, they have the same atlas, maximal atlas. Okay, so therefore the covering space of a Riemann surface inherits a unique Riemann surface structure such that the covering projection is a holomorphic map, and the whole projection becomes a holomorphic covering. Okay, so that is the whole point. And mind you, all this started with just taking a topological covering and making the assumption that the base of the covering has a Riemann surface structure, okay, alright. So that is what I wanted to emphasize, okay. Okay, so I just want to also make a couple of remarks to tell you that everything is really happening in the holomorphic category, okay. So if you remember, this is connected to when we were looking at the topological theory of coverings, there was this unique lifting property, okay, unique path lifting property, okay, and we also had this identification as of the fundamental group of the base space with a subgroup of homeomorphisms of the universal covering, okay. Now I just want to say that all this will happen in the holomorphic category, okay. So let me explain how this happens. Suppose I start with a covering map which is a holomorphic covering, okay. So suppose P from x tilde sub whole to x sub whole is a holomorphic covering, okay. So situation is like this, so I have x tilde, I have P, I have x, this is holomorphic, this is also holomorphic, that means these are Riemann surfaces, and of course P is the covering projection, okay. Now if Y is another Riemann surface, okay, and suppose from Y to x whole I have a map F which is a holomorphic map, okay. So suppose F from Y to x whole is a holomorphic map, from a Riemann surface Y, okay. Now assume that there is a lifting, assume that there is a lifting F tilde, okay, namely this diagram commutes, but assume that F tilde is only a continuous lifting, okay, okay. Assume F has a lifting F tilde which is only continuous, okay. So you look at what is happening. I have a holomorphic map of Riemann surfaces and it is liftable to a continuous map to the covering space. Then what happens is F tilde automatically becomes holomorphic, okay. The reason is because F tilde can be locally, it is F followed by an inverse for P, and P is locally biholomorphic, okay. So locally F tilde is holomorphic, that is just because locally I can invert P, and the inverse of P is also holomorphic. So the moral of the story is if you get a continuous lifting for a holomorphic map, it is automatically holomorphic, so it also comes into the holomorphic category, okay, that is the point. So then since P is holomorphic, is locally biholomorphic, F tilde also becomes holomorphic, okay. So you know, if you want to lift a holomorphic map, it is enough to lift it only to a continuous map, the lift will automatically become holomorphic, okay, you get that for free, that is just because P is locally biholomorphic, okay, that is one remark. Now what is the advantage of this remark? The advantage of this remark is that if you take the universal cover, then the deck transformation group which was identified as a subgroup of homeomorphic automorphisms of the universal cover will now be identifiable as a subgroup of holomorphic automorphisms of the universal cover given the natural holomorphic structure, the unique holomorphic structure that comes from below, okay, right. So in particular you see take a deck transformation So so you know take a deck transformation phi. So I have x, I have x sub univ, okay, and this is the universal cover, okay, all right. Take a deck transformation phi corresponding to the universal covering of the Riemann surface X, okay. So what is it? So X is a Riemann surface, so I will write as X sub whole, alright. X sub univ is universal cover that also gets a unique Riemann surface structure, so that this becomes a holomorphic covering. And now you see what is a deck transformation. See, it is actually a lift of P, which is a homeomorphism. So it is again a map from X to X sub univ, okay, which has a holomorphic structure, and it's a map like this phi, such that this diagram commutes, and phi is a homeomorphism. Okay, what is a deck transformation? A deck transformation is just a homeomorphism of the universal covering which respects the projection, okay. So it is a lift of P, okay, but it's a homeomorphism, so it's continuous. And I told you that since everything involved here is holomorphic, this phi automatically becomes holomorphic, okay, and a holomorphic homeomorphism is a biholomorphic map. Therefore what happens is that phi is not only an automorphism of the topological space underlying the universal cover, it is also a holomorphic automorphism of the unique Riemann surface structure that you get on this universal covering space. That is the whole point, okay. So then phi is an automorphism, a holomorphic automorphism of X sub univ whole, okay. So the moral of the story is, if you take the universal covering of a Riemann surface, alright, then the deck transformation group, which is the fundamental group which is identifiable with the fundamental group of the topological space below, actually becomes a subgroup of the holomorphic automorphisms of the universal covering, with the universal covering being given the natural one and only holomorphic structure that makes P the covering map into a holomorphic map, okay. So I mean these two remarks should tell you that we are completely in the holomorphic category, okay. So so that is why I am saying that this is a complete theory of holomorphic coverings, okay. So that is what I wanted to emphasize, yeah. So I will stop here.